Okay, let's jump right into this incredibly elegant explainer on the composite design pattern. Today, we're learning exactly how to tame those wild, tangled hierarchies of data. Seriously, if you've ever found yourself writing endless, messy conditional checks just to navigate your way through nested data structures, well, you are going to absolutely love what we're covering today. This whole concept is about taking complex, deeply nested code and transforming it into something incredibly clean and predictable.
We've got a really great roadmap for today. We'll start with the anatomy of a tree, move into the uniformity magic trick, cover the formal definition, then get into building the structure. After that, we'll look at a practical to-do list example and wrap it all up with the immutability advantage.
All right, let's kick things off with Section 1, Anatomy of a Tree, Root, Branches, and Leaves.
So, in our world of software engineering, a composite is really just an object that encapsulates a collection of other objects. It allows us to accurately model part-whole hierarchies without getting completely lost in the weeds of nested data. Just think about how often we actually deal with hierarchical data in real-world applications. We're talking file systems, user interface component trees, organizational charts, the list goes on. Managing these structures is notoriously tricky, because structurally speaking, you usually have to treat the individual parts entirely differently from the wholes that contain them. The composite pattern exists specifically to bridge that gap. It smooths out how we interact with all that nested complexity.
To make this concrete, just think about a standard family tree. Say I'm the root node. I have two parents, right? And each of those parents has two parents, my grandparents. Now, consider what happens if you trace dependencies downward from any single point in the structure. You essentially get an entirely new, self-contained subtree. If you look at just parent 1, well, from their perspective, they are the root of their own smaller tree, consisting of grandparent A and grandparent B. The whole tree is recursive. The pattern just repeats itself, no matter how far up or down the hierarchy you happen to traverse. Now, pay attention to the sharp contrast in the terminology here, because it's absolutely crucial. Leaves are the end of the line. They have 0 subbranches. In our family tree analogy, the grandparents, at least as far as we've mapped it out, are the leaves. They don't reference anyone further down. Composites, on the other hand, are the branches themselves that hold multiple nodes. Me and my parents, we're composites. We are nodes that contain other nodes. Understanding this functional difference between a standalone leaf and a container composite is literally the foundation we need to grasp the rest of this pattern.
Moving right along to Section 2, the Uniformity magic trick, replacing conditionals.
This is the painful reality pretty much every developer has faced at some point. Say we want an algorithm to collect the last names from every single person in our family tree. How do we avoid writing brittle code that constantly has to check if a node has children? Usually, you'd end up writing a massive, ugly block of code full of type checks. You'd be saying, okay, if this instance is a leaf, just give me the name. But wait, if this instance is a composite, loop through its children, and oh, hold on, I need to check if those children have children. You inevitably end up with deeply nested, highly brittle logic. As the hierarchy grows, your code becomes an absolute nightmare to maintain, and it's prone to bugs every single time a new level of depth is introduced.
But here's the solution, and it's incredibly elegant. By leveraging polymorphism, we can perform computation trivially. Why? Because we start treating leaf nodes and composite nodes uniformly, completely eliminating that ugly if statement logic. We ensure both types of objects implement the exact same interface. So when you ask for a last name, you literally just ask. You don't have to check what type of node it is first. The object inherently knows how to respond. The leaf just provides its name, and the composite knows to gather the names of its children. We're pushing the logic down into the objects themselves, which completely frees your main application code from managing all that tangled complexity.
Let's formalize this a bit. Section 3, the formal definition, the gang of 4. This classic definition from the pioneers of software design confirms our exact goal, and the absolute key phrase to lock onto here is treat uniformly. It ensures the developer using your code, the client, doesn't have to care at all whether they are dealing with a single item or a massive collection. They just call the method, and the data structure figures out the rest behind the scenes. When you make the client's life easier by hiding the complexity of the hierarchy, you dramatically reduce coupling in your architecture. Your system becomes more robust, way easier to test, and significantly easier for a brand new developer to onboard onto. It's a total game changer.
Okay, on to Section 4, building the structure, the UML blueprint.
The entire structure boils down to 3 crucial roles. First, you have the all-encompassing component interface. This is the central contract that absolutely everything in the tree must follow.
Second, the independent leaf, which acts as the worker and implements the operation directly. And third, the composite. You can think of the composite like a middle manager. It houses a list of other components. When you call the operation on a composite, it simply loops through its list of components and gracefully delegates the work, telling them to run their operations. That delegation is the secret sauce that makes the whole architecture tick.
Let's see this in action. Section 5, the to-do list example, generating HTML.
Imagine you're building an app where a project is a massive to-do list that contains individual to-do items, but it also contains entirely separate subprojects. And those subprojects can have their own subprojects, scaling down to an almost infinite depth of nesting. Our goal here is to write a single function that can render the entire nested HTML structure perfectly, no matter how deep or tangled that hierarchy goes.
So look at the distinct difference in how these handle their getHTML methods. Both the to-do leaf and the project composite share the same interface. But the leaf, which is just the simple to-do item, hands back its plain text wrapped in a standard list item tag. The project, on the other hand, outputs an opening unordered list tag, loops through all of its children asking for their HTML, and then outputs a closing unordered list tag. They are fulfilling the exact same contract, but they are executing entirely different behaviors under the hood.
The absolute magic here is the recursion. Think about it. The project doesn't actually know how to render its children. It just blindly calls their getHTML methods, trusting the pattern to drill all the way down to the leaves. If a child happens to be another project, well, that project will do the exact same thing. Open a tag, call its children, close the tag. The recursion naturally traverses the entire tree and strings together the precise HTML, bubbling the final perfectly formatted document all the way back up to the top level. It's brilliant.
Finally, let's wrap up with Section 6, the immutability advantage, architectural nuance. So if we want to add a new task to our to-do list, where does the code actually go? Do we put an add method in the base component interface so everything has it? Or do we only put it inside the composite class since leaves obviously can't hold new items? This is a classic trap in object-oriented design, and it forces us to make a really tough decision about where state mutation should be allowed to happen in a hierarchical structure.
While passing data through the constructor instead of mutating the object later solves this problem entirely. If you put add and remove in the base interface, you are forcing your leaf nodes to inherit methods they literally cannot use. What happens if someone calls add on a leaf? Does it crash? Does it silently fail? That is a direct violation of the interface segregation principle. The modern elegant solution here is immutability. Don't use add or remove methods at all. Just pass the entire list of children into the composites constructor at the exact moment you create it. Once the tree is built, its state is locked. It doesn't change. If you need a different tree with a new item, you just build a new one. It makes your codebase incredibly predictable and completely sidesteps the whole structural dilemma. 1. That is literally the number of unified interfaces required to process an infinitely deep, complex tree structure without ever checking an object's type. Just one single interface gracefully handles the standalone item and the massive million-item collection alike. So, I'll leave you with that thought. Go take a look at your own code bases. Find those tangled hierarchies, those deeply nested if statements checking if a folder has subfolders or if a specific task has subtasks, and see where the composite pattern can bring elegant simplicity to your work. Thanks for joining